Hi, so today we're still doing L'Hopital's rule, but the examples here are different than the ones that I went through before. So I want to make sure we're all okay to do them in case they show up on your AP exam. So for the first one, we have the limit of x times the ln of x as x approaches 0 from the right. So let's look at it as f times g. So if you have y equals x graphed, as x approaches 0 from the right, then you get an answer of 0. For ln of x, as x approaches 0 from the right, it keeps on going down, down, down. So we would say it's negative infinity. Well, this is one of our indeterminates. What makes this different is that we don't see that division before, but there is something we can do to make it a division problem. And that is to rewrite this as a complex fraction. So you may remember that you're always simplifying complex fractions. We want to now make this the opposite. So a lot of times I tell students you have to know your rules or properties inside and out, or backwards and forwards. This is definitely the case here. So the ln of x divided by 1 over x is the same thing as what we have here. These are equivalent expressions, especially now that I wrote that in. So if you have a function and it's being multiplied by a polynomial expression, then try to rewrite it as a fraction. So now, it's actually in a form of what we were doing yesterday. So if we were going to use L'Hopital's rule like we did yesterday, we would use this over this, and we're going to start to take its derivatives. This is the stronger version. So the derivative of ln of x is 1 over x. Okay, and the derivative of 1 over x is negative 1 over x squared. We've been taking derivatives for a while now. Even when we're going through integration, I have to write limit there, I apologize. So you may notice that by doing this, okay, that's kind of our goal for this particular problem. If we plug in 0, okay, for both of these, we're going to get something over 0. That in itself cannot be a value we work with, but, okay, let's not do that. Backwards and forwards. Let's rewrite this as one limit problem. So we started out making a complex fraction. Now we're going to simplify it. 1 over x divided by negative 1 over x is the same as multiplying 1 over x with a negative x squared. So if we simplify this complex fraction, then we're getting a negative x. Okay, so when you get a problem like this, first use complex fractions. Actually, either one of these two steps, okay, to rewrite it as one big fraction. See what you're working with. Maybe L'Hopital's rule will work the first time. If not, simplify that complex fraction you just made, okay, or its derivative thereof, okay. So at this point, it will work to find the limit because we can use the direct substitution and we get 0. Okay, so that's the answer to our problem. Let me know if you have any questions. And let's take a look at the second one. Okay, If you needed to stop or pause the video to make sure you got those notes from the last one, make sure you do. Now we're looking at number 2, and it's already in a fraction form. Now if our numerator is, let's say our function y equals e to the x, as x approaches negative infinity, it gets really close to the x-axis. So since 10 to the height is 0. Same thing goes for our denominator, let's call that g. Y equals e to the 2x. As x approaches negative infinity, it also gets closer and closer to the x-axis, so it's 0. So we do have an indeterminate, but let's take our derivative of our numerator, we get e to the x, and our derivative of our denominator, remember chain rule, we get 2e to the 2x. So we tried to do L'Hopital's rule, and I say tried because now we end up with the same sort of situation. This is the same thing as I was kind of discussing before. We get 0. Even over here, e to the 2x, as x approaches negative infinity, is 0 times 2, still 0. So it seems like L'Hopital's rule is not working. Now, in the last lesson, I told you to do it a few times. But if you notice that you end up getting a pattern of the same thing, and it's not giving you an answer other than maybe 0 or infinity, depending on the problem, then we can't use L'Hopital's rule. Okay, L'Hopital's rule does not work. Or repeating, doesn't work. Okay, so don't jump ahead and always be like, okay, this is a surefire way to do all my limit problems, because it's not. If you remember going back, if you could just simplify the expression, you can use that behavior to answer your limit. We're going to do that. So for number 2, e to the x over e to the 2x, same base, subtract the exponents. So I can use the limit of e to the negative x as x approaches negative infinity. Now, as you look at this function, think about transformation. X approaches negative infinity, the values keep getting bigger and bigger and bigger and bigger. So it may not have an exact value, but we can say the limit is infinity. So that's it for number 2. We got number 3 left. So infinity is a concept, and having 1 over infinity is kind of like saying you have 0. Okay? And this right here is an indeterminate. Okay, so we would want to approach this particular problem by using L'Hopital's rule. But we can't get there directly. We have to start using ln. And we have to do it for a function, the function we're looking at. So let's say y is equal to x to the 1 over x power. Okay, so what we want to use ln is actually right now, we want to use it on both sides of the equation. Now you may be thinking, where did this come from? Why am I using this? Well, as long as you use it to both sides of the equation, you're balancing it out, it's still equivalent. Okay, if you add 5 to the left, you add 5 to the right, it's equivalent. Do ln on the left, do ln on the right, equivalent, you're fine. The reason we want to use this is because we want to take this exponent and make it a product. And with properties of logs, we can do that. And natural logs are one of the best things we can use in mathematics. You can take the derivative quite easily. You can use your natural base. It applies to many applications like exponential growth and decay, which we went over. So, now what we're going to do is take the limit of both sides of this as x approaches infinity. So we're kind of applying what we want to answer in number 3. So I'm inserting it on both sides of my equation. Remember, balance your equation. Okay, and on the right-hand side, okay, this right here is the same as ln of x over x. Okay, on the left-hand side, well, that's still ln of y, but it's as x approaches infinity. Okay, so let's kind of take a look at how we can approach this. First, I'm going to take a different color here. Number 1 is going to be in blue. Okay, so let me erase this. We're going to use L'Hopital's rule on the right-hand side of the equation. Now, if we did infinity here, we'd have infinity over infinity. We could definitely do L'Hopital's rule. So that means I'm going to take the limit of the derivative in my numerator, which is 1 over x, and the limit of the derivative of my denominator, and that's just 1. Yay! So the limit of 1 as x approaches infinity is 1. And for the numerator, okay, think of 1 over x as x approaches infinity. Okay, we should know our common functions. So it gets closer and closer to the x-axis, we get an answer of 0. Okay, so for this particular problem, it simplifies to 0. I changed colors again to red. So now, number 2, I use the black marker here. Okay, we're going to now use e on both sides of our equation. You may be thinking, well, why are we doing this? Okay, this right here, we want to use e on both sides so that way we can pretty much work with e to the ln of y. We want y by itself. So this is interchangeable, okay? If we do e on both sides of our equation, I'm going to do that here. I will do it on the right-hand side, but I just want to discuss why it's interchangeable as it is. So let's pretend that y is some function. Let's go with a very easy function we all know y can equal, like x. Y equals x, nice line. And if we're to think of it that way and take the limit as x approaches infinity, and we do e of that, its answer is the same as if I were to switch this and do e to the ln of y. So that's the same as just x. The limit of x as x approaches infinity is infinity, just as much as this right here would turn out to be infinity if y was x. So just an explanation there. With variables, there is a proof that is true that we can switch up this order. So if I do e on one side of the equation, I'm going to do it to the other. And I could put it here, but we know eventually this is going to end up being 0. So I just want to make, I'm going to erase some of this, the left side of the equation, this expression, and on the right side of the equation, which we know turns out to be 0, that was over here, e to the 0. Sometimes it's not 0. If it's 1, then you get e to the 1. If it's e to the 0, well, its answer is just 1. So just take a look at what you have there. Now on the left side of the equation, we know that inverses undo each other. So it's the limit of y as x approaches infinity is equal to 1. But believe it or not, we just have what we wanted. We have what we need. Because if you remember in the very first step, we made y equal not just x, but x to the 1 over x power. So if I substitute that back in the very last thing I do, y is x to the 1 over x power, we just figured out the answer to the problem. It was 1. Okay, maybe it's a different value next time, but this is the steps to do it. Alright, so let me know if you have a question. Good luck, and enjoy L'Hopital's rule.